This is a lesson for partial fractions. Firstly, we're going to talk about improper algebraic fractions. What exactly are they? We know that a normal improper fraction is a fraction where the numerator is greater than the denominator. For example, 11 over 5. And this improper fraction can also be written in mixed form as 2 1 over 5. When you're talking about improper algebraic fractions, we are talking about two polynomials where the first polynomial, px, we call it, and the second polynomial in the denominator, qx, are such that the degree of polynomial for px is greater than the degree of q of x. What this means is that firstly we know that polynomials are of this form: ax power n plus bx power n minus 1 plus cx power n minus 2 and so on. So we have the highest power of x, in this case, which is n, and that's what we call the degree of that polynomial. So if the degree of the polynomial p of x, meaning the highest power that we have for x, is larger than the highest power that we have for the polynomial q of x, then we call it an improper algebraic fraction. And when we have an algebraic improper fraction, like this one right here, because here the degree of polynomial of p of x, which is the numerator, is 3, while for the denominator is 1, the highest power of x. When we have a fraction like this, what we can do is just divide this the long way. So polynomial long division, where we do this: x cubed minus 3x squared plus 7 and x minus 2 on the outside. Then we just divide the way we have done in the first topic. So x cubed divided by x is x squared, then x squared times x is x cubed, and x squared times negative 2 is negative 2x squared. Then we will subtract, so x cubed and x cubed goes away. Then negative 3x squared minus 2x squared, which is just plus 2x squared, which gives us negative x squared. Then we bring down the next degree, which is power 1, so plus 0x. Obviously we don't have it, so we'll write it as 0x. Then again we go through the same process. So negative x squared divided by x is negative x, then negative x times x is negative x squared, and negative x times negative 2 is positive 2x. Then you subtract again, and these cancel out. Then over here we have negative 2x. Then we bring down the last number, which is 7 plus 7, and again negative 2x divided by x is negative 2, then negative 2 times x is negative 2x, and negative 2 times negative 2 is positive 4. Subtract that, we have 3 at the end. Therefore what we have here is x cubed minus 3x squared plus 7 can be written as the multiplication of x minus 2 and x squared minus x minus 2 with a remainder of 3, so plus 3. Obviously this is the way we show the polynomial at the top, but we wanted to show this fraction right here. So we divide by x minus 2 on both sides. So x cubed minus 3x squared plus 7 over x minus 2 can be written as x squared minus x minus 2, which is your answer here at the top, then plus 3 over x minus 2. The remainder is a fraction with the denominator as the quotient. And as I said, express this fraction as the sum of a polynomial and a proper algebraic fraction. We have here the sum of a polynomial and a proper algebraic fraction right here. And that's example 1 done. Example 2 is just identifying what improper fractions or proper fractions are. So we'll go through these one by one. The highest power at the top is 0, the highest power at the bottom is 1, therefore this is going to be proper. The highest power of x at the top is 2, the highest power of x at the bottom is 2, therefore it's going to be improper. Obviously improper meaning the degree of the numerator polynomial is greater or equal to the degree of the denominator polynomial. And this one right here, again, at the top the highest power is 1, at the bottom the highest power is 1 as well, therefore improper here as well. At the top the highest power is 3, the highest power at the bottom is 2, therefore again improper. Here the highest power at the top is 1, the highest power at the bottom is 2 from x times x, x squared, therefore this is going to be proper. Here the highest power at the top is 3, the highest power at the bottom is 2 from here, x squared, therefore it's going to be improper. Here the highest power at the top is 5, the highest power at the bottom for x is 7, therefore it's going to be a proper algebraic fraction. And finally here the highest power at the top is 4 and the highest power at the bottom is 2, therefore this is going to be an improper algebraic fraction. Next example, dividing another improper algebraic fraction into the same form, sum of a polynomial and an algebraic proper fraction. This is improper because the degree at the top is 3, the highest degree, and the highest degree at the bottom is 2 coming from x times x. So for that we divide. Obviously we have negative, so that applies to the numerator. Negative x cubed minus 2x squared plus 0x plus 7 divided by, opening this bracket, we get x squared plus 3x plus 2. Then we can divide these. Negative x cubed divided by x squared is just going to be negative x. Then negative x times x squared is negative x cubed. Negative x times 3x is negative 3x squared. And negative x times 2 is going to be negative 2x. Then we can subtract that, these cancel out. Negative 2x squared plus 3x squared is going to be x squared. And 0 plus 2x is going to be 2x. Then we bring down the 7 and we repeat the process. So x squared divided by x squared is just 1. 1 times x squared is x squared. 1 times 3x is 3x. 1 times 2 is 2. Then we can subtract. These cancel out. 2x minus 3x is negative x. And 7 minus 2 is positive 5. So what we do have is negative x cubed plus 2x squared minus 7 over x plus 2 x plus 1 is equal to the answer right here. So negative x plus 1 plus the remainder and the quotient as the denominator. So negative x plus 5 over x plus 2 x plus 1. That's how we will have it. Next up we look at partial fractions. In IGCSE we learned how to add and subtract algebraic fractions by finding the common denominator. And that's what we'll be doing for these three cases. So for case 1 is just a normal fraction plus another fraction. And the way we convert this into the common denominators is we multiply the fraction by the other denominator for each one. So for 4 over x minus 2 we'll multiply it by x plus 3 over x plus 3. And for this one we're going to multiply it by x minus 2 over x minus 2. What that does is both of them get the denominator of x plus 3 x minus 2. Then the 5 is with x minus 2 multiplied, and the 4 is with x plus 3 multiplied. And then what we can do is just add both the fractions because they will have the same denominator. The other case is when you have one of them being a normal expression and the denominator of the other fraction is a square of that original expression. So what we have to change here is just this fraction right here, where we will take our 3 over x plus 1 and multiply it by x plus 1 over x plus 1. What that will do is get the numerator as 3x plus 1 and the denominator as x plus 1 squared. Then we have common denominators and we can just add them. So 3 times x plus 1 plus 2 over the denominator of x plus 1 squared. Then the last case is when we have a square in one of the denominators. Again, this is like case 1, but what we have to see is what happens to the numerator. So in our numerator we will have one of them being multiplied by a second degree polynomial, x power 2, and the other one being multiplied by a first degree polynomial, x power 1. And that's the only difference. Now why is this important? Is because we are going to do the reverse. So we're going to have this originally and we want to get this in return. We're going to have this originally and we want to get back the original addition. We will have this originally and we will want to get the original one that's there. So for this, we look at these three cases differently. Case 1 is where both of them are a polynomial of degree 1, where it's simple. If you have px plus q over ax plus b times cx plus d, that's going to change to a over ax plus b, so one of the brackets, plus b over cx plus d, the other bracket that we have in the denominator. And obviously this can be extended to 3 or more fractions as well, where if we have a third bracket in the denominator, we'll just add the third term c over ex plus f. The second case, when we don't have two brackets, we will have only one bracket but a square bracket. Then remember from case 2, this happened as a result of one of the fractions having a normal polynomial as the denominator and the other fraction having that same polynomial but squared as a denominator. Therefore, if you see something like this, then to convert it into partial fractions, we will take our a, the thing that we're going to find, so you're going to see examples in the future, over that denominator without the square, so ax plus b, plus b over that denominator including the square, so ax plus b squared. This is an example for case 1. So this will be distributed into a over one of the denominator brackets, so 2x plus 1, plus b over the other one, so x minus 3. And when we add these two, what we're doing is multiplying by 2x plus 1 over 2x plus 1 to this one, and multiplying by x minus 3 over x minus 3 to the left one. We're multiplying with the other denominator. Then on the left we will have a x minus 3 over 2x plus 1 x minus 3 plus b 2x plus 1 over x minus 3 2x plus 1. Then because these have the same denominators, we can just add them up. We'll end up having a x minus 3 plus b 2x plus 1 over 2x plus 1 x minus 3. And that is going to equal to the original fraction, which is 2x minus 13 over 2x plus 1 x minus 3. Then we can just equate the numerator with the numerator right here. So we can put the x terms together. Ax plus 2bx from this thing right here is going to equal to 2x. And on the other hand, we have negative 3a plus b is equal to negative 13 from this thing right here. And this is just a case of simultaneous equation where a plus 2b equals 2. We can get rid of the x's because we're only dealing with the coefficients. A plus 2b equals 2 and negative 3a plus b equals negative 13. Solving this simultaneously will give us that a is equal to 4 and b is equal to negative 1. Therefore, what we can do is go back to our original format, which was this thing right here, and change our a's and b's. So our a is going to now become 4 and our b is going to now become negative 1, and that is going to be our partial fraction. 4 over 2x plus 1 minus 1 over x minus 3. That's going to be our partial fraction for this original fraction that we had. So we have 2x minus 11 over x minus 4 square. This is case 2. And this is going to be expressed as a over x minus 4 plus b over x minus 4 squared. And obviously when you add these two, what happens is you want to multiply by x minus 4 over x minus 4 here. So a over x minus 4 times x minus 4 over x minus 4. And then plus b over x minus 4 squared. What this will do is this will end up becoming a x minus 4 over x minus 4 squared plus b over x minus 4 squared. Then we can just add these. So a x minus 4 plus b over x minus 4 squared, because that's the denominator, and that will equal to 2x minus 11 over x minus 4 squared. So what we're doing here is just comparing this to this right here. So what we have is, after expansion, we have ax minus 4a plus b is equal to 2x minus 11. The only x term on the left is a, therefore a will equal to 2. Then we can find b from that as well. So negative 4 times a, which is 2, plus b equals negative 11. Therefore negative 8 plus b equals negative 11. Therefore, we have that b is equal to -3. So remember, this was our original format. We've gotten the value of a and b, with a being 2 and b being -3. And therefore, this is going to be our partial fraction from this original fraction that we had. This is an example of a mixture of case 1 and case 2, where we have two brackets multiplied with each other, but one of the brackets is a square. So we're going to combine the information from both. So our partial fraction is going to look like this: a over the first bracket, x plus 2, plus b over the second bracket without the square, 2x plus 3, plus c over the third bracket including the square, so 2x plus 3 squared. There's a trick to skip all the middle steps here, where you just take the numerators and multiply by the original one's denominator, each one. So this one times x minus 2 and 2x plus 3 squared, where x minus 2 and x minus 2 will cancel out. This one as well times x minus 2 times 2x plus 3 squared, where this will cancel out, one of the ones that is squared with the denominator. And this one as well times x minus 2 and 2x plus 3 squared, where this entire thing will cancel out. So we will remain with a, 2x plus 3 squared, plus b, x minus 2, 2x plus 3, plus c, x minus 2. And that is going to equal to the numerator from the original fraction. So 1 minus 9x minus 8x squared. For this, we get that a, 4x squared plus 12x plus 9, plus b, 2x squared minus x minus 6, plus c, x minus 2. Now we can split them according to these three terms. So the x squared terms, we have 4a from this, plus 2b from this, and that will equal to -8 from this right here. Then the x terms, so we have 12a from this, then we have -b from this, and we have plus c from this, and that will equal to -9. Then finally we have 9a minus 6b minus 2c, and that is equal to +1. And this is a triple simultaneous equation. We can solve this as well. Solving this will give us that a is equal to -1, b is equal to -2, and c is equals to +1. Then what we can do is take these values and substitute in our original format. So here we'll have that a is -1, we'll have that b is -2, and we'll have that c is 1. And this is going to be our partial fraction from this original fraction that we had. Case 3 is slightly different from the rest. So when we have the inside of a bracket that has an x squared, which cannot be factorized, then the fraction will be split up using this rule right here. And let's see it in an example. So this thing right here will be split into a over x minus 1, the one without the square. And for when the denominator has a square, we add a bx plus c over our x squared plus 2. Then what we will do is just multiply by the denominators throughout. So a times x minus 1 and x squared plus 2, and bx plus c times x minus 1 times x squared plus 2. Here this is going to cancel out, and on this side this is going to cancel out. What we will have remaining is a x squared plus 2 plus bx plus c x minus 1, and that will equal to the original numerator, which is 8 plus 2x minus x squared. We can expand this even further. So ax squared plus 2a plus bx squared minus bx plus cx minus c. and that will equal to 8 plus 2x minus x squared. Then we can just compare the terms that are alike. So x squared with the x squared and the x squared. So we have a plus b equals -1. Then the x values, so -b, c, and 2. So we have that -b plus c equals 2. And we have that 2a minus c equals 8. So 2a minus c equals 8. This is again a triple simultaneous equation. And from that we get that a is equal to 3, b is equal to -4, and c is equal to -2. So in that original form that we had, we have that this fraction right here can be expressed as 3 over x minus 1 plus -4x minus 2 over x squared plus 2. And that's going to be the way that this original fraction can be written in partial fractions. This is the last case, which is improper fraction, where it's going to be like a two-step thing. So firstly, we know how we deal with improper fractions. We need to do long division. So here we'll start off by doing long division. 2x squared plus 5x minus 11 divided by x squared plus 2x minus 3. 2x squared divided by x squared is just 2. Then 2x squared plus 4x minus 6. Subtract that, this goes away. 5x minus 4x is just x. -11 minus -6 is just -5. So here 2x squared plus 5x minus 11 over x squared plus 2x minus 3 will be equal to 2 plus x minus 5 over x squared plus 2x minus 3. But we can still factorize this further. And to factorize this, we will get x plus 3, x minus 1. So we end up having x minus 5 over x plus 3, x minus 1, which obviously is case 1. So we go into our a over x plus 3 plus b over x minus 1. Then skipping a few steps, we have a x minus 1 plus b x plus 3 is equal to x minus 5. Therefore, a plus b equals 1 from the x's, and negative a plus 3b equals -5. From here, we get that a is equal to 2 and b is equal to -1. So this will end up becoming 2 over x plus 3 plus -1 over x minus 1. So then basically this fraction ends up becoming 2 plus 2 over x plus 3 plus -1 over x minus 1. And that is it for this example. Finally, what we have here is an application of partial fractions. So it can be used to evaluate sum of certain sequences. So given that an algebraic fraction 1 over x times x plus 1, and they've already done the partial fraction part, and it can be written as 1 over x minus 1 over x plus 1. Find the sum of the first n terms in the series 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 and so on. So as you can see, this series is just this fraction right here. And we can write it as this thing right here. So what we will have is 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4 plus 1 over 4, and you get the gist. What happens with this, as you can see, is you have -1/2, then you have +1/2, and these cancel out. Then you have -1/3 and +1/3. Again, these cancel out. And this keeps on happening until you get to the nth term, where the term right before that is going to be 1 over n minus 1 minus 1 over n. Then the final term plus 1 over n minus 1 over n plus 1. And obviously this cancels out with the previous one. And this 1 over n cancels out with the +1 over n. So what we're left with is the first term, which was 1, and the last term, which is 1 over n plus 1. And that is going to be the sum of the first n terms of that series. When you're looking at it to infinity, this is when n goes to infinity. So what happens here is that the denominator becomes extremely large, making the fraction extremely small. And by extremely small, I mean very close to 0. Therefore, we basically will have 1 minus 0, which will equal to 1. So that will be the sum to infinity.